Bismillahirrahmanirrahim. Today we are going to discuss green synthesis and recycling. Green synthesis and recycling is a part or tool of green chemistry, and green chemistry is that branch of chemistry which is integrated in all the branches of the chemistry, because this gives the concept about the reversal of harsh chemicals or reversal of orthopogenic activities towards the nature. So let's have a look at the green synthesis and recycling. Recycling and green chemistry. Recycling may bring green thoughts to mind. For many of us, the word chemistry conjures up thoughts of bad chemicals, mad scientists, and incomprehensible concepts. Even the definition of chemistry, the science that deals with the composition and properties of substances and various elementary forms of matter, is enough to make most of us either yawn or not want to learn more. But let's put all of our preconceived ideas about chemistry behind us and take a look at where chemistry is heading. It is in the early stage of going green. And let's take one step further and see how this new green chemistry can even make recycling greener. Although the realm of chemistry may deal with elementary forms of matter, its application goes way beyond the chemical industry. Applied chemistry spans industries as diverse as pharmaceutical, transportation, agriculture, law enforcement, material, and electronics. In fact, the list of its application a recycled chemist copy is probably almost endless. Globally, chemistry is a $2.4 trillion industry. Although the chemical industry often parallels the growth and trends of broad industrials, it was inside the chemical industry itself where the march to green trail began. How did the chemical industry arrive at such an important crossroad? Let's see. Somewhere along the bumpy road of modern industrialization, society realized that widespread use of chemicals often came with the price of toxin in the environment. In the early 1960s, when information surfaced about the toxicity of the pesticide DDT, which is also known as dichloro-diphenyl trichloroethane, footsteps towards the path of green chemistry began to march. Used extensively during the World War II to control insect-borne diseases like malaria and typhus, DDT also soon became the major agricultural weapon for the combat of crop-destroying insects. According to the Environmental Protection Agency, in 1959, alone nearly 80 million pounds of DDT chemical was used in the United States of America. But indiscriminate use of this chemical would soon change when in 1962, the book by Rachel Carson, Silent Spring, brought to light how DDT was harmful to birds and to the food chain. In 1972, the United States of America Environmental Protection Agency banned the use of DDT. So, What replaced it? Nothing too green, that's for sure. DDT was replaced with another harmful chemical that is called TEPP. This is the abbreviation of tetraethylpyrophosphate and parathion. And this is an insecticide that is extremely lethal to birds and to human beings. While for the past 40 years, regulations has been the main focus in the control of harmful chemicals, the replacement of DDT with other toxic chemicals illustrates just how faulty the regulatory approach can be to preserve the environment and safeguard public health from harmful chemicals. Chemistry itself had to change. And in the early 1990s, two scientists began to change the direction of chemistry and called it green chemistry. Scientists Paul Anastas and John Werner looked at chemical development and applications differently than anyone had ever done before. Whereas industry and government focused on how to deal with chemical waste, these green pioneers questioned why the waste should exist in the first place. Their 12 principles of green chemistry is the worldwide framework for the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. Although green chemistry has been on the science scene for 20 years, putting it into the wide-scale practice will take much longer. To make green chemistry useful, it must be applied to broader industry. Today, it is estimated that only about 1% of the chemical industry production is based on green chemistry. So, we have a long way to go before its application becomes widespread. Since green chemistry strives to reduce or eliminate hazardous substances, its application can be very beneficial to any industry, and that includes the industry of recycling too. Now let's see how recycling benefits the environment. Recycling reduces the use of natural resources by reusing materials. 94% of natural resources used by the Americans are non-renewable. Non-renewable natural sources use has increased from 59% in 1900 and 88% in 1945. Recycling saves non-renewable sources. For example, by not recycling paper, 80% more wood will need to have been harvested by 2010 to meet the growing paper demand and consumption demand. However, through active paper recycling, only 20% more wood will be needed to be harvested by 2010. It takes 95% less energy to recycle aluminium than it does to make it from raw materials. Making products from recycles result in energy saving. Recycled steel saves 60% energy production. Whereas recycled newspaper saved 40%, recycled plastic saved 70%, and recycled glass saved 40% renewable energy. Using scrap steel instead of virgin oil to make new steel saves 40% less water and creates 97% less mining waste. Now, let's see how recycle benefits the economy. Incineration, 10,000 tons of waste creates one job, while landfilling the same amount creates 6 jobs. Recycling the same 10,000 tons creates 36 jobs. So, green chemistry with reference to recycling is a benefited process for the economy and for the environment. The National Recycling Coalition reports that recycling has created 1.1 million jobs. That is the $236 billion in gross annual sale and $37 billion in annual payroll. By meeting the state's 50% recycling goal, California is expected to create about 45,000 recycling jobs compared to 20,000 new jobs slated to be created from the manufacturing sector. Another data provides that employs more than 9,000 people is more than 200 recycling enterprises. About half of these jobs are in the recycling-based manufacturing sector. These businesses represent more than $500 million in value to the state's economy. To keep things simple, let's take a look at a few ways that chemistry is helping or can help in the future recyclables like plastic, papers, glass, and electronics. So first we are going to deal with the plastics. For those of us who recycle plastic, plastic recycling has become a part of our everyday lives. Each year, Howard of PET, that is the PET, or it is also known as polyethylene terephthalate, plastic containers in the form of drinking bottles, condiment jars, and even microwavable food trays find their way into our recycling bins. PET, the highly recognized plastic resin code, is on many of the grocery items we purchase. According to the NAPCOR, that is the NAPCOR, in 2008, over 5.4 billion pounds of polyethylene terephthalate bottles and jars were available for recycling in the United States of America. That's a lot of PET plastic, but did you know that the print PET, soda pop, or water bottles you recycle cannot be recycled into another bottle? PET plastic bottles and jars are almost always made from virgin plastic. Recycled PET plastic normally leaves the food industry and ends up in textile. Why? Because current PET recycling methods are unable to break down the long plastic polymer chains into the smaller molecules required to recombine and produce new bottles and other products. Most PET recycling is a mechanical process which results in lower quality plastic that cannot be used for most beverage and food containers, while the chemical recycling of PET does exist and does result in high quality recycled plastic. It is an expensive process and is not economically viable due to the low cost of virgin PET resin. If it is less expensive to make virgin bottles, industry will not use a potentially polluting, more expensive chemicals method to make bottles out of recycled PET plastic. Greener chemistry may soon resolve that problem. Last year, researchers at IBM and Stanford found that a molecule inspired by a vitamin B1 called a carbene facilitated the breakdown of PET plastic quickly and in a cost-efficient manner. The resulting recycled PET has sufficient quality to be used again for the production of bottles and other food containers. As with all chemical reactions, no reaction has 100% efficiency. There are still ancillary products left over from the process. According to what I understand, in case of this particular process, the byproduct of the carbene chemical breakdown of PET are less harmful to the environment than those of traditional chemical processes. The one certain thing is that if this process becomes commercially available, the recycling rate of PET plastic will increase and the use of a virgin resin will decrease. This process will allow a closed loop PET bottle system to become standard practice. Now let's see about the paper. According to the Forest and Paper Association, the United States of America paper industry used about 31.3 million tons of recovered paper last year. That kept about 47% of our paper waste out of landfills. With all that recycling, what happened to all the inks that was printed on those millions of magazines, documents, and newspapers? Well, it may have literally washed on down the river. When it comes to paper recycling, the de-inking process is very chemistry intensive and requires chemicals like sodium hydroxide, hydrogen peroxide, and chelating agent like DCPA and EDTA. It is the use of the chelating agent that is of most environmental concern because these chemicals bind with heavy metal ions like copper, manganese, and iron and wash them out with the waste effluent from the recycling plant. Heavy metal poison rivers. New research at North Carolina State University is exploring how sugar and protein-based surfactants can be used effectively to remove ink during the paper recycling process and keep toxic metals out of the waste stream. This is the green chemistry at its best. Now let's see about the cycle, what green chemistry says about glass. Until recently, large pieces of glass like those found in our 60-inch LCD TVs always contained the heavy metal arsenic because arsenic is required to remove bubbles from the glass during its manufacturing. Most PET recycling is a mechanical process which results in lower quality plastic that cannot be used for most beverage and food containers. While the chemical recycling of PET does exist and does result in high quality recycled plastic, it is an expensive process and is not economically viable due to the low cost of virgin PET resin. If it is less expensive to make virgin bottles, industry will not use a potentially polluting, more expensive chemicals method to make bottles out of recycled PET plastic. Greener chemistry may soon resolve that problem. To best capture the value out of a waste stream, green chemistry is being used to separate out individual valuable metals. Research conducted at the Shanghai Jiao Ton University in China has developed a process that can capture all the heavy metals and separate out valuable copper. But copper reclamation is just a start. Many scarce materials like titanium, lántalum, and hafnium are also used frequently in organic materials or in electronic components. Recapturing these metals is an important goal of green chemistry. Reclamation of valuable metals reduces the demand for mining and all the environmental hazards that come along with it. These are just a few examples how green chemistry can help to make recycling greener and even improve its profitability. The small steps that are being taken now can make great environmental strides possible in the future. Governments, universities, and industries must work together to promote the development of economically viable green chemistry solutions. Since the application of chemistry cuts across a myriad of industries, it will take commitment and cooperation between the industries to keep heading down this road. As with the story of DDT, government regulations of the chemical industry does not always result in a greener solution. Government can provide support to help make this great change by providing research and development incentives to business conducting the work in green chemistry. As citizens, we can do our part too by purchasing greener products. Many consumers could like household cleaners, paint and food packing are now available in greener, less polluting, more recyclable formats. We can afford to turn it back. Organic synthesis is a special branch of chemical synthesis and is concerned with the construction of organic compounds via organic reactions. Organic molecules often contain a higher level of complexity than purely inorganic compounds, so that the synthesis of organic compounds has developed into one of the most important branches of organic chemistry. There are several main areas of research within the general area of organic synthesis, that is the total synthesis, semi-synthesis and methodology. Somewhere along the bumpy road of modern industrialization, society realized that widespread use of chemicals often came with the piece of toxins in the environment. In the early 1960s, when information surfaced about the toxicity of the pesticide DDT, which is called as dichlorodiphenyl trichloroethane, footsteps towards the path of green chemistry began to march. Used extensively during the World War II to control insect-borne diseases like malaria and typhus, DDT also soon became the major agricultural weapon for the combat of crops destroying insects. In science and technology, one among the rapid developing concepts in the latest year is nanotechnology, which has brought tremendous development. A nanomaterial which comprises distinct physiochemical properties has the potential to develop new systems, structures, devices, and nanoplatforms with impeding bids in extensive variety of disciplines. Nanomaterials are particles that are in nanoscale size, and they are very small particles with improved thermal conductivity, catalytic reactivity, non-linear optical performance, and chemical stability due to their large surface area to volume ratio. Its quality has attracted many researchers to locate novel techniques for their synthesis. A total synthesis is the complete chemical synthesis of complex organic molecules from simple or commercially available or natural precursors. The total synthesis may be accomplished either via a linear or convergent approach. In a linear synthesis, often adequate for simple structures, several steps are performed one after another until the molecule is complete. The chemical compounds made in each step are called synthetic intermediates. They more complex, a different approach may be preferable. Convergent synthesis involves the individual preparation of several pieces. These pieces are the intermediates, which are then combined to form the desired product. We have a different implementation of green chemistry. We have different aspects of the green chemistry. Green chemistry or green synthesis may be introduced in the following areas, such as microwave induced green synthesis. We can make ultrasound assisted green synthesis. Scientists can carry out biocatalysts in organic synthesis. Phase transfer catalysis in green synthesis. Researchers can work on aqueous phase reactions in green chemistry. We can also study and research on the energy efficiency in green chemistry, application of green chemistry in organic synthesis. So be happy with green product shopping.